heat capacity along with molar heat capacity and specific heat capacity. And also we will be talking about the relationship between the heat capacity at constant pressure and heat capacity at constant volume. We know that if we have a substance, we provide more heat, higher the temperature difference will be. So if any substance is at 25 degrees Celsius, we provide say 25 kilojoules, then there will be some temperature, may temperature rises to 25 plus X. And if we provide say 50 kilojoules, then it will be 25 plus say 2X. Okay. It means the temperature rise is proportional to the heat. So these are proportional to each other. Now, when we remove the proportionality sign, then we introduce the constant. This constant is actually the heat capacity. And this heat capacity is of all the matter, whatever we have. So suppose we have 1 kilogram, then this will be heat capacity of 1 kilogram. If we have 5 kilograms, this will be heat capacity of 5 kilograms in that case. So when we say heat capacity, it is the heat capacity of the entire mass, whatever we have. So obviously it will not be constant for a particular type of material because it will depend on how much mass we have of that material. So for example, if I have 1 kilogram of iron, it will have some heat capacity. If I have 5 kilograms of iron, it will have 5 times the heat capacity, the previous case. So this is the relationship you need to memorize. Q is equal to C into delta T. We will be using this in numericals. So you need to memorize the relationships here. From here we can say that delta T is equal to Q by C. And if we provide constant heat, now we are talking about different materials. Suppose we are talking about copper and say iron, or maybe iron and wood. The materials are different and we provide same amount of heat. In that case, what we can say that if heat is constant, then delta T is inversely proportional to the heat capacity. Delta T is inversely proportional to heat capacity. So we say when C, that is heat capacity, is large, a given amount of heat results in only a small temperature rise. So if this is large, the delta T will be small. Questions directly based on this relationship will be asked. So if we have two different materials, for one material we have C large. For that material, the rise in the temperature will be less. Okay, so larger the heat capacity, smaller the change in temperature. C is directly proportional to the amount of substance. This is something I have already told you, that if we have 1 kilogram, there will be some heat capacity. If I have 5 kilograms of same material, it will be 5 times of that heat capacity. So heat capacity depends on the amount of the substance. It is directly proportional to that. Now we talk about molar heat capacity. As the name suggests, now it is not of the entire amount. It is exactly of 1 mole. So it will be constant for a material. For a material, molar heat capacity will be constant because in 1 mole there will be a specific amount of that material. So molar heat capacity of a substance is the heat capacity for 1 mole of the substance and is the quantity of heat needed to raise the temperature of 1 mole by 1 degree Celsius. So the definition is very much similar. Okay, so the previous definition, if I explain the previous heat capacity, in that case, if I had 1 kilogram, whatever heat is required to raise the temperature by 1 degree. Remember, this is always 1 degree, whether it is heat capacity, whether it is molar heat capacity, or whether it is something I will be talking about a specific heat capacity after this one. In all cases, the definition includes the temperature difference of 1 degree Celsius or 1 degree Kelvin. The difference is same whether it is in Celsius or whether it is in Kelvin. So if I talk about heat capacity, then the heat required to raise the temperature of 1 kg or heat required to raise the temperature by 1 degree of 5 kg, that will be heat capacity. Here in molar heat capacity, we always have 1 mole of a substance. And of this substance, we need to raise temperature by 1 degree. The heat required is known as molar heat capacity. So we know that from previous heat capacity, Q is equal to capital C into delta T. Molar heat capacity is represented as C subscript M, just to indicate it is molar heat capacity. Now try to understand the simple mathematics here. Suppose you have some amount of material. This is some amount of material. Okay? And the heat capacity, total heat capacity is C. And suppose here you have 4 moles of this substance. So 4 moles, this one for 1 mole heat capacity will be Cm, 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 Cm. For each mole, the heat capacity will be Cm. So what the relationship you will get? You will get the number of moles multiplied by molar heat capacity. That will give you total heat capacity. So total heat capacity will be the molar heat capacity multiplied by how many moles are there in that substance. So suppose we have n moles instead of 4, that was just for example. If we have n moles, we will multiply by n to get the total heat capacity. It means this C I can write as Cm into n. Cm into n will give me total heat capacity. This I can substitute in place of this C. I can substitute Cm into n. So I get relationship for molar heat capacity. This is important formula. You need to memorize. Again, this one is important formula. From here, Cm into n equals to C. You get molar heat capacity in terms of total heat capacity. So if total heat capacity is given, just divided by number of moles, you will get molar heat capacity. Simple formulas and relationships you need to memorize, and you will get the numerical done very quickly. Next one is specific heat capacity. When we say specific heat capacity, and whenever you hear this word specific, it is for unit. Here we are talking about mass, okay, total mass, total amount, or just 1 mole. In case of a specific, it will be unit, means 1 gram, mostly 1 gram. 1 unit does not necessarily mean that you are restricted to gram. You can say 1 kilogram also, but in most of the cases it will be 1 gram, because in chemistry the calculations are normally in gram. For example, when you calculate moles, you say total mass divided by molar mass, and the mass there is in grams. Similarly here, now the definition is very simple. We will again raise the temperature by 1 degree Celsius, but of 1 gram only. Instead of 1 mole, now 1 gram. So specific heat, also called specific heat capacity. So remember, here capacity might not be written. You need to understand, if you get a specific heat written, it is actually specific heat capacity. Is the quantity of heat, that is Q, required to raise the temperature again by 1 unit, but of 1 gram only, 1 unit mass. By 1 degree Celsius of 1 unit mass. Now what we did in case of molar heat capacity, we are doing the same thing. Suppose this is the entire substance, okay, and the heat capacity, total heat capacity is C, and there are say 10 or say 25 grams, okay. Each gram has its own heat capacity. This heat capacity, specific heat capacity, is written as lowercase c, but normally to understand, few guides use capital C and subscript S just to indicate the specific heat capacity, but most of the books you will see written as lowercase c. Lowercase c and uppercase C just creates confusion, so I am writing it as yes. So if 1 gram has heat capacity as Cs, that is the specific heat capacity, to get total heat capacity, you will have to multiply this by number of grams. So this is heat capacity of 1 gram. If you multiply it by number of grams, that is mass. Here M is mass, okay, not moles. For moles we used N. M is mass. We will get total heat capacity. So again, we will do the same thing what we did in case of molar heat capacity. In place of C, we will write C into M, lowercase c, or you can write CS if you want. And we get again the formula, important formula for specific heat capacity. So if I am saying, I'm just repeating, if I am saying heat capacity, then I will say Q will be equal to capital C into delta T. If I am talking in terms of molar heat capacity, then C I can write as Cm into number of moles and into delta T. If I am talking about specific heat capacity, then Q will be equal to specific heat capacity multiplied by how much mass I have, to T. Because in case of molar heat capacity, this is the total heat capacity. In case of specific heat capacity, this gives us total heat capacity C. So you remember this formula and you can write these two formulas from there. Now the relationship between Cp and Cv. Here we are talking about total heat capacity C, capital C, at constant pressure and at constant volume. And we are using the same formula to get the relationship. What is the relationship we are going to obtain? This is the relationship. Cp minus Cv is equal to R. Cp is heat capacity at constant pressure, Cv is heat capacity at constant volume, and R is universal gas constant. So we will use the generic formula Q equals to C into delta T. Here we have substituted P just to indicate it is at constant pressure. Otherwise it is same formula for constant pressure and for constant volume. Same formula at constant pressure, at constant volume. Now we know that the heat change at constant pressure is actually the enthalpy of the reaction. If you remember, UV was delta U, that is change in internal energy. So the heat difference at constant volume gives us change in internal energy. Heat change at constant pressure gives us change in enthalpy. So we know this relationship. So we will substitute these values. QP we will substitute as delta H and QV we will substitute as delta U. So this gives us QP. QP is delta H equals to Cp into delta T from this relationship, and from this relationship QV we are writing as delta U. We get delta U equals to Cv into delta T. Now we know the relationship between delta H and delta U. Delta H equals to delta U plus delta Ng RT. We will substitute if it is for 1 mole. So if it is for 1 mole, we are substituting Ng as 1, number of gaseous moles 1. So in that case, delta H will be Cp into T, delta U will be Cv into delta T, and Ng is 1. We will have R delta T from here. Now you can see that delta T will get cancelled. Delta T will get cancelled and we will get Cp minus Cv equals to R. The only point you need to remember here is that it is for 1 mole. If we are talking about n mole, then in that case we will say nR, n times R. Normally you will be asked to derive this relationship only, Cp minus Cv equals to R, but in numericals there might be n number of moles. So you will use this relationship, and I advise you to memorize the relationship with n. The only thing is that if it is 1 mole, obviously this n will be 1. So you will get the same relationship and Cp minus Cv equals to R. It is better to memorize this relationship, Cv minus Cv equals to nR. Otherwise, there is a chance that you can skip the number of moles in the numerical. Then there are few questions which appear specifically in competitive examinations on the atomicity of a gas in terms of specific heat. Okay, Cp and Cv. So sometimes Cp and Cv will be given and you will be asked what is the atomicity of the gas. So in terms of Cp and Cv, we will be talking about. For monoatomic gas, Cp minus Cv ratio will be approximately 1.66. So when you calculate this value, it might be 1.62, 1.63, or it might be 1.7 also, right? But it is close to 1.66. You will mention that as monoatomic gas. For diatomic gas, the ratio will be 1.4. Again, it will be close to 1.4. It may not be exactly. It can be 1.38. It can be 1.42 also. And triatomic gas, this ratio will be 1.30. Now, in case of 1.30, it will be 1.29 or 1.31. Right? The difference will not be as high as it can be in case of monoatomic and diatomic. So you need to be cautious here. However, in most of the cases, the calculation will be very, very simple. Okay. They are not testing your calculation skills. They want to test whether you know the concept or not. So monoatomic gas, for example, can be helium. Helium has just one atom. Diatomic gas can be N2. There are two atoms in one molecule. Triatomic gas can be O3, ozone, 3 atoms of oxygen in one molecule. On that basis, the question might not directly say monoatomic, diatomic. It might say which one is for nitrogen, which one is for ozone. So obviously you need to relate it in terms of atomicity.